Yeah, we'll probably get through I think last week we covered page 1, essentially the top half. The bottom half of page 1, I'll explain a little bit stuff that you don't need to know. Because when you look at the bottom of page 1, it's kind of like doo-doo-doo-doo, kind of weird. Page 2, 2 ways to represent sound, and then amplitude, frequency, and phase, frequency and period, and wavelength and frequency. I think we'll get through that stuff today. So, yeah, at any rate, I've already started the recording here just to have that going. But so last time we talked about, what sound waves are, squeezing and separating of molecules, and I talked about longitudinal waves and transverse waves. And when you look at the bottom of page 1, let's get that puppy out of the way here. So what I'll do is I'll share screen, and let's see, and we'll get the PowerPoint up there that explains it. Now, when you look at the bottom of page 1, it's dealing with this particular slide. I'm sharing screen here. And whenever you see the word sine, S-I-N-E, just think bends or curves, because sound waves are shown as bends or curves. Think of the word sinuses, okay? And when you look at the circle here on the left, it's got 360 degrees. Similarly, when you look at a sound wave on the right, it's got 360 degrees. Think of a sound wave as just something it's just bent over this way, and it makes a full circle. I mean, that's essentially it. And you can see the axes on the diagram, and think of a sound wave as a circle. It says if you swing the two opposite ends of the wave together, you have a circle, blah, blah, blah. Okay, that's all fine and dandy. And then it says think of a swing where one cycle is a total forward and then back again. And notice that the speed is fastest right at the ground, slowest at the top and bottom. All that means is notice how the sound wave is actually kind of more pointed on the top and more pointed on the bottom, and it's not just an even circle like that. And I guess what that's referring to, if you think about it this way, it refers to this fact. See how the black in the center, it's most black right in the dead center, and it's kind of gray, and then it fades to white? I think that's what it's showing. So this wave here on the bottom is not really an accurate indicative indication of the stripes on the top. It would probably be a wave more looking like this, or a wave looking more like this on the left. On here, that would be more indicative of the sound wave that we draw of the actions that's actually taking place in the atmosphere with atoms. That's all I care about. Who cares? Let's go to page 2. Not going to ask that anyway. Just next. All right. When we look at the top of page 2 in the notes, if I can find my darn cursor here. Okay, let's move down to page 2 in the notes. There we go. 2 ways to represent sound. Now, we've talked about sound waves. That's one way to represent sound. And that's the most basic way to represent sound. As a hearing instrument specialist, you probably will not be dealing much with sound waves. We talk about sound waves so that we get a better idea of what the heck sound is. And that's the purpose. A part of the purpose of this course is to describe basically what sound is, the sound waves, and what it does, how it moves, and stuff like that. As hearing instrument specialists, I'll go to the PowerPoint here. You're going to look at sound more in terms of stuff like this. I'll move my way down here, and you'll look more at sound in terms of stuff like this here. I'll pull this up. This is a spectrum. Now look at the axes on a spectrum. A spectrum is showing you a slice of time. In other words, when you look at the horizontal axis, it says frequency. When you look at the vertical axis, it says amplitude. So where's time on here? Remember, sound takes place in 3 dimensions: frequency, intensity, and time. But a piece of paper is flat. it's got two dimensions, width and length. So I can't show all three dimensions of sound on a flat piece of paper. I can show you sound waves, or I can show you spectra. So here's a spectrum. Time isn't included on a spectrum. When you think of a spectrum, think of a spectral slice. In other words, if I go to a sound wave, I'm going to show you a complicated, here, a sound wave. I'll move up to the top here, and we'll just talk about, I'll pull this guy up here. Here's two sound waves, okay, on the top and on the bottom. Now look at what it says on the axes here. Amplitude or pressure, same thing, amplitude or time. Look at another one. Amplitude and phase here, time. Look at another one here. Amplitude, time. Sound waves are shown as amplitude over time. And when you think of a sound wave, think of a loaf of bread. A loaf of bread from the end to one end. A spectrum is when you're taking a slice out of the bread and turning it sideways so you can see the raisins in it. Okay? So a sound wave doesn't show frequency. It shows amplitude and time. A spectrum shows amplitude and frequency. So when you think of the sound of the spectrum, look at this. I'm going to draw a line here, and just think of a line going, whoa, I moved my whole picture here. Think of moving a whole line, okay? If I got to this, if I could draw a line down my thing, I just went slice right down the center, and then turned it sideways so you could see it. That's what a spectrum is. And we'll be going to spectrums a whole lot more in this course, because HISs look at sound in terms of spectrums or spectra. You're going to look at what's coming into a hearing aid and what's coming out of a hearing aid. In other words, let's look at the most important sound we can possibly think of regarding sound. And for humans, have a look at this. This is a spectrum of speech. That's the sound that your hearing aid wearers care the most about, speech. And when you're looking here at the horizontal, frequency, and decibels, amplitude. And look at how these three lines, it's like a mountain going down. This is the low frequencies of speech, the sounds that come from your throat, the vowels. Oh, here it says, my internet connection is unstable. Hope you're still with me. Anyway, and then look at how it slopes down here. So it means in the low frequencies where my cursor is, there's more amplitude. And in the higher frequencies, there's less amplitude. And that makes perfect sense, because what sounds louder in speech, vowels or consonants? And the answer is vowels. So you should place vowels, A, E, I, O, U, right where my cursor is circling, right here. And when you think of the letters S, F, and K, S, Sh, K, put them over here, because they're higher pitched. You see, they're higher frequency, and they're softer. So we'll get to this much later on in the course as well. I'm just giving you a preview. So when you read at the top of page 2 in your notes, 2 ways to represent sound. Waveform, that's sound waves. It's labeled with 2 axes, time on the horizontal, amplitude on the vertical. Easy to see sound as it changes over time, but you cannot see individual frequencies very well. That's true. In other words, if we go to the top here and you pick a sound wave, here's a couple of sound waves right here. And if you think about this, look at the top wave. What's the frequency there? You'd have to go, well, geez, I don't know. What's the time length? Okay, is it 1 second? Oh, okay, we'll call it 1 second. You're going to have 1 wave, 2, 3, 4. I guess it must be 4 cycles per second. I guess, because I'm counting 4 bumps. But it doesn't just tell you. You have to figure that out. Okay, frequency isn't listed here. Okay, it's there, but you'd have to figure it out. You have to go, what's the time, and now count the bumps. Oh, okay, that must be the frequency. All right. So you can see changes in the sound wave. Even think of those weird movies that you see when they're showing you sound waves on the screen. You're looking at sound waves. Those are sound waves. And you can see the changes taking place over time as the person's talking. Yep, but it's hard to tell what the frequencies are because you have to go, oh, what's the length of time? And now how many bumps are taking place per unit of time? Well, a spectrum is a lot kinder that way because a spectrum shows frequency on the x-axis or the horizontal axis, it says in your notes, and it shows amplitude on the vertical. So it's easy to recognize all the individual frequencies in a sound, but it does not show sound changing over time. And that's why I call a spectrum a slice. Think of sound waves as a loaf of bread. Think of a spectrum as a slice out of the loaf, turned sideways so you can see the nuts and raisins. That's really the best way that I can describe it. And it says in italics here, more on these ways to represent sound later on in the section on complex sounds. We'll get there in about a month from now. We will be there. All right? Cool. I'll share screen again, and we'll go to the second section on page 2, and that is talking about the 3 ways to represent sound. And let's look at this particular picture right here. This is a good one because it shows you everything. The top is showing you amplitude. The middle is showing you frequency. The bottom is showing you time or phase. These are the 3 dimensions in which sounds takes place. So look at the top pair. Are they the same in frequency? And you have to look at that and go, yeah, because if the length is 1 second, they each have the same amount of bumps per second. The same amount of cycles. Remember, a cycle is 1 condensation, 1 rarefaction. 1 cycle is 360 degrees. Okay, they have the same amount of wavelengths, the same amount of cycles. So they are the same hertz, capital H-E-R-T-Z, capital H, small z. Okay, the middle panel is showing you another pair of sounds. But the top pair, back to them, how do they differ? They differ in amplitude. They differ in decibels. One's louder, the top one. So if you were thinking about sound in terms of the very first picture I showed you in this presentation, if you thought about sound in terms of these patterns from the tuning fork, loud sounds, the darker would be darker and the white would be whiter. Here's another way of showing you. Whoops. The darker would be darker and the white would be whiter if this was a really intense sound. If it was a soft sound, then the black lines would be just kind of more gray and the white would be lighter gray. Okay? So when you're thinking of intensity, it's the height of the sound wave. That's how we draw it. The taller wave would indicate that this black was really bunched together and that the white was really separated. That's what it means. So moving along over to there again, I quite like this slide because it shows you everything. Now look at the middle pair. The middle pair are similar in amplitude. They differ in frequency. And the bottom pair, so the top one here is lower in frequency. The bottom one is a higher pitch. So this must be a bass tone, and this must be a treble tone. But they're similar in height. Okay, now look at the bottom. The bottom pair shows you the same frequency, the same intensity. They're just opposite in phase. So if you played these 2 sounds together, you'd have the sound of one hand clapping. Silence. They'd cancel each other out. And in fact, when people design sound rooms, okay, when people design auditoriums, and theaters. These are acoustical engineers, and they design it so that the sound from the speaker and then the echo from the wall, okay, that those don't cancel each other out. Otherwise, you're going to get a dead spot, a lousy quality of sound in certain areas of the theater. So acoustical engineers design very carefully to prevent dead spots where the reverberation or the echo is, the sound wave is in opposite phase to the sound of the speaker or the actor. So phase, intensity, frequency. 3 ways to represent sound. We'll read the notes here. Note the different amplitudes. Top panel, different frequencies, middle panel, and the different phase, the bottom panel. So these are the 3 dimensions of sound. Pure tones, these are all pure tones. There's another thing to put a star by, because what we're covering mostly at the beginning of acoustics is pure tones. So when you look at the top pair, these are each a single frequency. The top one here is 1 frequency. Here's the similar frequency. It's just softer. So if this was 1,000 cycles per second, 1,000 hertz, this might be 1,000 hertz, but we know if we called this 1 second, we actually had 1, 2, 3, 4, I think 5, 6, I think like 9.5 or something like that. I'm too lazy to count them. Okay, but we don't normally listen to such low frequencies, do we? We listen. What's the range of human hearing in terms of frequency? We hear as low as 20 hertz, 20 cycles per second, and the highest treble sound we can possibly hear is about 20,000 cycles per second. So 20 and 20, remember, 20 hertz to 20,000 hertz. Cats can hear higher, like up to 60,000 hertz or something, and bats even higher, okay? Elephants, the opposite. Elephants hear low frequencies, large ears, lower frequency sounds, and we'll talk about the animal kingdom in just a bit here. But reading in your notes here, 1/3 of the way down page 1, pure tones are simple sounds with single sine waves. In all actuality, these are quite rare. The only time you listen to a pure tone is when you're getting a hearing test under headphones, and the examiner is presenting to your right ear 1,000 hertz, and you're raising your hand. When did you hear 1,000 hertz? Okay, then he or she makes it 30 decibels. Did you still hear it? Then they make it 20 decibels. Did you still hear it? Then 10 decibels. Oh, I can't hear it anymore. Go up to 15. Oh, now I heard it. Okay, now let's put 2,000 hertz, and they'll do it again. And then finally, they'll test the other ear. So you're getting hearing testing in one ear and then the other ear, and they're presenting pure tones. And guess which pure tones they present? Why don't we just jot this down? Have you had any knowledge of hearing testing or audiometry so far? I'm not sure if you have. Maybe you're getting that already in another course. Are you or not? Do you know, Audra? Have you taken any of it or not yet? Okay. No. I'll tell you this. We test you at 7 octave frequencies. When you get a hearing test, they test you at 1,000 hertz, and then 2,000 hertz, and then 4,000, and then 8,000. And notice the numbers have doubled each time. When you double the cycles per second, you've gone up an octave. That's what octaves are, when you double the frequency. So if you have 1,000 hertz, what's 1 octave higher? 2,000. What's 1 octave higher? 4,000. And a higher octave? 8. And then they stop getting higher and they go to the lower frequency side and they test you at 125 hertz. Now, what's 125 hertz? That's low C on a piano. And then they test you at 1 octave higher, 250 hertz. That's middle C on a piano. And then they test you at 500 hertz, and that's high C on a piano. And then you're done. Then they test the other ear. So 1,000, 2,000, 4,000, 8, and then 125, 250, 500. That way they've tested you at 7 octave frequencies. And can you tell that music is really on the lower frequency side, isn't it? Music is on the lower frequency side. It's the lower 3 frequencies. Low C, middle C, high C. And it tells you that music is kind of na-na-na, na-na-na-na. Yeah, Ted, keep your daytime job. But speech is way higher than music, okay? So only the vowels of speech, the sounds from your larynx, only those are akin to music. The lips and popping consonantal sounds are way out of the range of music. And that is where elderly lose their hearing first. It's called presbycusis. Presbyterian, Church of the Elders. Presbyopia, your arms aren't long enough to see the page, hits you when you're 40. Presbycusis, trouble hearing treble. And they can't hear treble, they'll say young people mumble these days. Anyway, down to the third, down on page 1, most sounds are complex. In other words, they're not pure tones. So I'll get out of this guy here and go to the notes, see if I can. Okay. There we go. We'll look at the notes here. Most sounds are complex, right where I'm graying there. Okay, most sounds are comprised of many pure tones combined together. And look what it says there. For example, noises, voices, musical instruments, traffic, door slams, all kinds of sounds are complex sounds. All right, cool. Now let's move to the middle of page 2. We'll talk about the relationship between frequency and period. Now, I will first show pictures, and then we will talk about it. So when you look at this particular slide in your PowerPoints, you can see a wave, a single cycle wave beginning at 0 degrees phase, 90, 180, 270, and back to 360. Now the A stands for amplitude. Okay, that's the height of the wave. And the period, PR, stands for the time. Now, when you think of the word period, think of a watch on your wrist. What was the time it took to complete one cycle? Well, if this is 1 second, and you had one cycle taking place in 1 second, the period is 1 second. It took 1 second. Okay? Now, if I go to another sound, this is more in terms of phase. And here they're talking about wavelength. And that's what we'll finish today at the bottom of page 2, is the length of the wave. So you can talk about the physical length of the wave in inches or feet or centimeters and meters. That's one way to talk about waves, sound waves. And the other way to talk about sound waves is, what was the length of time? The time it took to complete one cycle. So here you got 0 degrees phase, 360. This was your period. It took 1 second in that particular case to hear the sound. Let's see, amplitude, period. Okay. Yeah, here we go. So what's going to be the period of this? Look at the top sound. I'm going to make it bigger so we can see it. Okay. If there are 1, 2, 3, 4, 5, 6, 7, 8, 9.5. Okay, let's just round it to 10. Pretend it's 10. Okay, if this was 1 second, what was the period of that top wave? What was the time it took to complete one cycle of that particular wave? Well, if the whole length is 1 second and you have 10 cycles per second, I guess the period must have been 1/10 of a second. Okay? So in this particular sound, it's 10 hertz, we'll call it, 10 cycles per second. So what was its period? 1/10 of a second. All right, can you see the relationship? It's inverse, we call that. The higher the frequency, the shorter the period. Let's look at the bottom, or the middle panel here. In the middle panel, we'll count the number of cycles in this top wave. 1, 2, 3, 4. Let's pretend it's 5. So it's 5 hertz. So what's its period? If the length of the black box is 1 second, and you had 5 cycles per second, what was the time it took to complete one single cycle? I guess 1/5 of a second. 5 hertz, 1/5 of a second. Okay, so it's that relationship. Also notice that its wavelength physically is longer as well. So think 2 things change with frequency. The period changes and the physical length of the wave changes. And here's the general relationship. I'll stop sharing and I'll just kind of say this. As frequency increases, gets higher, as you move from bass to treble, as you start getting more cycles per second, the period gets shorter and the wavelength gets shorter. So, increased frequency, decreased period, decreased wavelength. As you move to bass sounds, lower frequencies. You've got long wavelengths and longer periods of time. The period is the time it takes to complete one cycle, and the wavelength is the physical length of the wave. All right? And you can think about wavelength in the animal kingdom. What do bats emit? Bats are blind. They're flying around at night, and they're catching bugs. How the hell do they do that? Well, they emit really high-pitched sounds. And those high-pitched sounds have tiny, tiny wavelengths. They're really, really short because they're so high up in pitch. And high-frequency sounds bounce off of things like radar. Ding, 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 ding. So they bounce off the bugs, and that's how the bats know where the bugs are. That's how they can eat bugs while they're flying. And you think of the opposite. Elephants emit really low-pitched sounds, like 20 hertz, 10 hertz. We can't even hear it. And low-frequency sounds are so darn long, they're like from here to across the street in length. And low-frequency sounds bend around objects. They don't bounce. They bend around rocks and trees, over the hills and down into the next valley. And that is how elephants can track each other's movements. You'll see one train of elephants walking like this from a helicopter or a plane, and guess what? A couple miles away, you'll see another train walking the same way. Zoologists wondered how the heck they did that. Now we know they emit low-frequency sounds that bend around objects, whereas high-frequency sounds bounce off of things. And this has lots to do with the whistle that takes place in hearing aids. When people turn up a hearing aid and it whistles. How come it whistles? Because high-pitched sounds are leaking out. They're bouncing off of your eardrum, bouncing between the hearing aid and the walls of your ear canal, and they're leaking out, and they're getting picked up by the mic, amplified again, leaking out, picked up by the mic. It's like you in a sound with a mic, and you move too close to the speaker, and you get that they get that loud feedback, and that's because sound from the speaker, not just from your voice, but sound from the speaker is coming into the mic. You're getting a loop. High frequencies do that. They cause feedback because they bounce and they're short. We'll get more into that anyway. Let's read in our notes and just read now what it says right in our good old notes here. I'll get out of this slide here and I'll choose there. Okay, let's read here. Frequency and period. And then you're going to look at the bottom where it says frequency and wavelength. You see the two sections? So we'll first talk period, then we'll talk wavelength. Period first. Time. Frequency, the number of times something happens per some unit of time. For sound, frequency refers to the number of cycles per second. Hertz, Hz, 1 hertz, 1 cycle per second. For example, a sound with a frequency of 100 cycles per second is 100 hertz. Period, the time it takes to complete one cycle of sound. For example, if a sound is 1 hertz, then its period is 1 second. If a sound is 100 hertz, then its period is 1/100th of a second. And so, put a star by this one, frequency and period are inversely related. As frequency is increased, period is decreased. So here's the formula. And when I ask, not if, but when it gets asked on quizzes and midterms, this is how you figure it out. Frequency is 1 divided by the period. Period is 1 divided by the frequency. That's the inverse relationship between period and frequency. So for an example, if I said, oh, what's the frequency of 1,000 hertz? Or I should say, what's the period of 1,000 hertz? Period equals 1 over the frequency. Okay, period equals 1 divided by 1,000. 1 divided by 1,000. Here, I'll get my calculator here. See if I can figure that out. Turn on this, oops, turn on my good old calculator. 1 divided by 1,000 equals, okay, you can't see that because my calculator sucks when it comes to showing the, anyway, it says 0.001. Okay, so it's basically period is 1 over frequency. Frequency is 1 over the period. When you read at the bottom, in the very middle of page 1, humans hear from as low as 20 hertz to as high as 20,000 hertz. Our very best hearing, look what it says here where I'm highlighting. Our very best hearing is right between 1,000 hertz and 4,000 hertz. That's the sweet spot. That's right where the consonants are of speech, between 1,000 and 4,000 hertz. And nature, or God, has given us the best hearing sensitivity to hear those particular sounds. And you know why? You know why we hear 1 to 4,000 hertz the best? Look at your ear. The shape of this weird looking thing, the bends and folds in it. What a weird looking device. Well, like a wine glass at Christmas. When you're doing that, you're making the whole wine glass go. Your outer ear has the shape it does because it resonates with those high pitches. And that is why we hear 1 to 4,000 hertz the best. The fewest decibels are required for us to just barely hear those frequencies. When we get to lower or higher frequencies than those, our hearing sensitivity isn't quite as good anymore. We still hear them, but we require more amplitude to just barely hear them. It's just something to think about. It's how the ear is literally married to speech. The speech and hearing are connected. All right, now we can move to the bottom of page 2, and we'll talk about wavelength versus frequency. Now we'll leave period alone, and let's look at the physical wavelength, right where I'm highlighting there. When you're getting into this topic, we need to talk about speed of sound. Wavelength, it says here, also, just like period, wavelength is inversely related to frequency, just as same as period. But period is talking about the time it takes to complete one cycle. Wavelength is talking about the physical length of the sound wave. So it says here, as frequency increases, wavelength gets shorter. Recall, period is also inversely related to frequency. And it says here, wavelength involves the speed of sound. Now have a look at what this says, because this also is something that's asked on midterms and quizzes constantly. You're going to see 3 different little formulas here. And if you watch with me, it says wavelength equals speed of sound divided by frequency. Frequency equals speed of sound divided by wavelength. And speed of sound equals frequency times wavelength. And if you're going, oh my God, look at the right of side, it says there. 5 is equal to 10 divided by 2. 2 is equal to 10 divided by 5. 10 is equal to 2 times 5. It's the same relationship. In this course, there is no trigonometry, there is no algebra, there is no calculus. It's simple arithmetic. The stuff that we all learned in 6th grade, fractions, multiplication, addition, division, and subtraction. So wavelength on the top here, look what it says there, equals speed of sound divided by frequency. That's like saying 5 is equal to 10 divided by 2. Next, frequency equals speed of sound divided by wavelength. Well, that's like saying 2 is equal to 10 divided by 5. And at the bottom, speed of sound equals frequency times wavelength. Well, that's like saying 10 is equal to 2 times 5. Same as it ever was, okay? Now, here's the constant, speed of sound. In air, speed of sound is 340 meters per second. In air, speed is about 766 miles an hour. So look what we're talking about here. Miles versus metric. Okay, we're talking USA versus the rest of the world. Because USA deals in miles. The whole rest of the world talks in kilometers. All right? Just so we are all clear, science talks in terms of metric. But you don't have to use metric. You can do the same thing in feet. So let's go for an example. Let's just look at the bottom of the page here, where it says formula. Wavelength equals speed of sound divided by frequency. So what we're doing is the very top one, because we want to know what the wavelength, that's what we're trying to figure out here. Okay, so for 100 hertz, wavelength equals, okay, 340 meters per second. 343 to be exact, but 340 is good enough. 343 meters per second divided by the frequency, which is 100. Okay, what's the wavelength of 100 hertz? 3.43 meters. Now, a meter is about a yard. Okay, a meter is about 3 feet. So it's going to be 3.5 meters, 3.5 yards in length. Whoa, think about that one once. 100 hertz tone is going to be 3 times 3 feet and then add another half. So about 10.5 feet long. 10.5 feet long. That means one condensation is about 5.25 feet, and one rarefaction is about 5.25 feet. That's pretty, see what I'm saying? But when you get to 1,000 hertz, that wavelength gets shorter and shorter and shorter. But now you can see where the elephants that are emitting sounds like 10 hertz and 20 hertz. If 100 hertz is about 10 feet long, okay, then when you start getting half of that, well, now you're getting 20 feet long. And half of that, now you're getting 40 feet long. So the lower the frequency, the longer the wavelength. That's why I say 10 hertz is like from here to the middle of next week. I mean, it's way across the street in length. You're talking big. All right. All right, now we'll stop sharing here and take a peek at what it says. In feet, let's figure it out in feet. Wavelength equals 1,130 feet per second, because that's the speed of sound in air in terms of feet. 343 meters per second in feet, 1,130 feet per second, divided by 100. Well, that's 11.3 feet. Told you, it's over 10 feet long. All right, so in terms of feet, 100 hertz is 11.3 feet long. In terms of meters, it's 3.43 meters. Let's look at the bottom ones here where it says 250 hertz and 8,000 hertz. For 250 hertz, 343 meters per second divided by 250, well, that equals 1.37 meters. Or in terms of feet, 1,130 feet per second divided by 250 equals 4.5 feet. So if 100 hertz is 11.3 feet long, that's 100 hertz. 250 hertz, you've gone double and a little bit more in terms of the frequency, and you've cut the wavelength by less than half, 4.5. Okay? So you think of the middle C tone on a piano, no, just average middle C on a piano in music. Well, that tone is 4.5 feet long. Let's go to 8,000 hertz. That's the highest frequency that we test human hearing. Because recall, we test hearing from 125 hertz up to 8,000 hertz. Well, 340 meters per second divided by 8,000 is 0.04 meters. In other words, 4/100ths of a meter. Or 1,130 feet per second divided by 8,000 is 0.14 feet. So simply use a calculator and simply push the buttons and you can figure out period and wavelength just because you know the frequency. Conversely, if I gave you the wavelength, you'd be able to figure out what the frequency is because here, frequency equals speed of sound divided by wavelength. Either way, just do the arithmetic, boom, You get your answer. And then it says at the bottom here, important concept for those who fit hearing aids. Low frequencies bend, high frequencies bounce. Low frequencies have long waves that bend around objects. Phase differences important. In other words, think of elephants. Highs have short waves that bounce off of objects. Think of bats. So now let's just review what we've covered here. Three main things, essentially. We talked about two ways to represent sound, waveforms or sound waves, and spectrums or spectra. Then we reviewed the three elements of sound, amplitude, frequency, and phase, or you could call those the three dimensions in which sound takes place. And then we covered frequency and period, and we said period is the time it takes to complete one cycle, and we said they are inversely related. And then we moved off of that and we talked about the physical length of the sound, and that too is inversely related to frequency. And when you're talking about wavelength, we need to bring in the speed of sound. That's when you got this particular set of formulas. So remember the two sets of formulas. I am highlighting this because from experience last year or previous years, it's when people forget the simple formulas that when I throw a calculation at you, they get lost. And it's actually not that difficult as long as you memorize the formulas. Period is 1 over frequency. Frequency is 1 over period. Speed of sound and wavelength and frequency are all related as well. Wavelength is speed of sound over frequency. Frequency is speed of sound over wavelength. Speed of sound is frequency times wavelength. Let's kind of preview where we're going to go next week. When you look at the speed of sound, let's just talk about the speed of sound once. Check this one out. The velocity of sound. At room temperature, sound speed is about 340 meters per second. About 1,130 feet per second, or 1,238 kilometers an hour, or 766 miles an hour. The speed of light is 100 million times the speed of sound in air. Light travels about 300 million kilometers per second, or about 186,000 miles per second. All right, really okay. The speed of sound is at least 4 times faster in water than it is in air. So when whales are talking to each other or dolphins are communicating underwater, the speed of sound in water is 4 times faster than it is in air. And if you look at the speed of sound in metal, in steel, in a railroad track, speed of sound in metal goes 14 times faster than it does in air. The speed of sound depends on the medium through which it travels. The more dense the medium, the slower the speed of sound. And you might be thinking, well, that doesn't make sense because a railroad or the metal of a railway track is way more dense than air. I can move my hand through air, but if I get whooped upside the head by a metal bar, I'll get injured or I'll die. Okay, metal bar is way more dense. The speed of sound is slower with increased density, but, big capital B, but the more elastic a medium is, the faster sound is. Now, what's elasticity? The stiffness. So density is the mass. Elasticity, don't think of rubber bands. Elastic is in physics, elasticity means stiffness. And steel is also way more stiff than air. Okay, and the elasticity or stiffness of steel far outweighs its greater density. So even though sound waves go slower the more dense an object is, They go faster the more stiff an object is. And the stiffness of steel compared to air far outweighs its greater density compared to air. And that is why sound goes faster through steel than it does through air. That's just a little piece that will help separate the A's from the B's in 110 acoustics. I'll just throw that puppy at you, and it's going to be one of the, so, but don't worry when you're starting to get inversely related to square root of density directly, I couldn't care less. Think of density as the mass, think of elasticity as the stiffness. Every object through which sound travels, every medium through which sound travels has density and it has elasticity. It has mass and it has stiffness. All objects, air, water, steel, my cup, my ear, anything through which sound travels has mass and stiffness. And it's the relationship of mass and stiffness that determines the speed of sound, but it also determines the resonance. Think about your ceiling. You think you got noisy neighbors upstairs and they're playing loud music. What's going to come through your ceiling? The bass guitar and the drums, because your ceiling is dominated by mass. And mass is what's going to resonate with low frequencies. The cymbals and the high frequencies are not coming through the ceiling, okay? Because your ceiling is dominated by mass or density as opposed to stiffness. We will be getting to these things much more later on in the course. But at any rate, if we go to the PowerPoint slides and we look at what we've covered today, we've gone through a whole bunch of stuff. All right, so you're looking at this guy here. We talked about time, period. Look at this. Here's another 360 degrees, another single cycle. It's just a different phase. This one here, this one here. This one here started in a rarefacted phase and then condensed. Doesn't mean it's not a nice wave. It's just a different. Here's another wave that started here at 90 degrees phase, but it also is a single cycle, because now you're back to where you started. So this is just showing you 3 different phases of a single cycle. Here again is 2 tones at the top. They differ in frequency. They're the same in amplitude, and they started at the same phase. These 2 sounds, okay, are the same in frequency. They're the same in amplitude. They started at different phases. The bottom pair shows you the same frequency. They started at the same phase. They're just different amplitudes. Again, this slide is showing you quite similar stuff to this slide, just showing it to you in a different way. Amplitude, period. Amplitude, period again. Okay? But also we can look at wavelength. Often in books they draw wavelength like the Greek letter lambda. Don't ask me why. It's just, who cares? Wavelength is often seen, though, in physics as this weird Greek letter. And again, period, wavelength. Period, wavelength. Both of these are inversely related to frequency. Here you're looking at a low frequency sound, a mid frequency sound, a high frequency sound, and the same length of time taking place, just more cycles per second, and the wavelengths get shorter as you're getting higher, higher, higher up. So this would be bass, mid, treble. Here's the spectrum I showed you again. This shows you a spectrum of a whole bunch of sounds together. A low-pitched tone, another one, another one, another one. And look at these tones. These are harmonics. Here's the fundamental, the low frequency in the complex sound. And here's the next frequency. It's double the frequency, so it's 1 octave higher. And then you have another harmonic, and another harmonic, and another harmonic. And these are all getting softer and softer and softer as the frequency increases. In this particular spectrum, you've got a whole bunch of different frequencies, and they're all harmonics of that fundamental frequency. They are all equal multiples of this particular fundamental frequency. But let's talk octaves. Hey, here's the bottom one. That one's 1 octave higher. What's 1 octave higher yet? 400, because you double it. What's the next octave? 800, because you double it. Okay? The differences between harmonics and octaves we'll cover mañana, later on. Here's another series of complex sounds. 3 different spectra, A, B, C. They might be from 3 different musical instruments. They all have the same fundamental frequency and different on the same harmonics. But look at this, they're different amplitudes. And that's what's going to make different timbre or quality. This might be a trumpet, this might be a clarinet, this might be an oboe, who knows? This is showing you a broad band spectrum. It's got a whole bunch of frequencies in it. This one's showing you not much energy in the low frequencies, more energy in the high frequencies. So there's all kinds of lies that I can tell you, okay? Lots of things. And this one here is talking about, this one here, don't worry about this slide, talking about wavelength in air versus water. It doesn't matter. This one here is talking about the Doppler effect. We'll talk about this next week. How come when you're hearing an ambulance racing toward you, it's going, when an object is coming toward you, the pitch gets higher, and when the object goes away from you, the pitch gets lower. Go to the Indianapolis racetrack. Okay, when a car is moving toward you, you've got the speed of sound plus the speed of the car. So the wavelengths get squeezed. You're hearing a higher pitch. When the car goes past you, you still have the speed of sound minus the speed of the car. So the waves get elongated. You hear a lower pitch called the Doppler effect. This one's kind of cool though, breaking the sound barrier. And when a jet goes through the speed of sound, it's going Mach 1. This means the waves are becoming, you've got your sound waves going 340 meters per second or 1130 feet per second, and now that jet is catching up with that speed of sound. So all the waves get bunched together. They're all squeezed because the wave is, the jet's going the speed of the sound. So all the sound from the jet is squeezed into a ball, and all of a sudden the jet goes through that, and then you've got this big rarefaction vacuum behind the jet, and the whole crunched up ball of molecules fills in that vacuum behind the jet, and that's the sonic boom. Give you another example of a sonic boom that's more what we experience, just for the heck of it, and then we'll tune off. You ever taken a towel like this and have someone snap you on the legs of the towel? Hurts, don't it? You know why that hurts so bad? Because the tip of the towel snap is breaking the sound barrier. That's why a crack of a whip and the snap of a towel, that little hurts really bad because that tiny little tip of the towel is actually breaking the sound barrier. And that snap is actually a tiny little sound barrier being broken. Anyway, thought I'd finish with that little flourish there, because it's true. So look what we covered. Page 2. Got that puppy done today. And if you look at the top of page 3, we talked about the speed of sound. And we'll start over on this when we begin next week. We'll start kind of at the top of page 3. And we'll quickly review the Doppler effect. We'll quickly review the breaking the sound barrier. But also put a star by this density and elasticity thing. When you're thinking density, think mass. And actually, I should write that in myself. Density, mass. And when it says elasticity, I'm making an arrow and I'm calling it stiffness. That's exactly what I wrote right here. Okay? These are concepts that are going to appear again and again and again. But you got your mass and stiffness. God, when I'm looking at it, it goes backwards. I don't know why, but anyway, you know what I mean. Mass is density refers to mass, elasticity refers to stiffness, and every object that transmits sound has its own mass and stiffness. These properties determine the speed of sound through the object, but they also determine the resonance. All right. as they say in Britain, cheerio. Yeah, quite. We'll see you next time, eh? Well, that sounds more Australian. Anyway, all right. We'll talk to you later. Okay, we'll finish this unit next week. So we will have spent 3 weeks on Unit 1. And then Unit 2 is called the decibel. I always call it the decibel from hell. We'll spend 2 weeks on that guy. Maybe 3, but probably 2. And then we move into complex sounds, where we will be talking more about the characteristics of speech, because it's really important that hearing instrument specialists have a good handle on the properties of speech, because that's the sound that hearing aids are mostly amplifying. And then we move into a midterm. You'll have a midterm exam, and then we move into psychoacoustics, or our perceptions of sound intensity, which is loudness, and your perception of frequency, which is pitch. So the scientist talks about what is the intensity, what is the frequency, and the artsy fart says, oh, what's the pitch? How loud was that? Okay, so you've got the two sides. Psychoacoustics is perception, but we are right now on the physics side. We'll move into the perception side because that gets us into the hearing test. And that gets us into what's called the audiogram, upon which we lay our hearing sensitivity of the right ear and the left ear. The right ear we always draw as O's. The left ear we draw as X's. We play tic-tac-toe. And we mark down the intensity in decibels that it takes to just barely hear the different frequencies. Most people have a treble hearing loss, so most hearing aids provide mostly treble. That's why hearing aids don't just make sounds louder. Hearing aids, like glasses, are a prescription, and you are going to be the one prescribing it. You're going to change the sound of the hearing aid so it's like a mirror image of the person's hearing loss. So you're going to sculpt the spectrum of the hearing aid. The sound that the hearing aid's putting out needs to be a mirror image opposite of the person's hearing loss on the audiogram. So you'll be doing the hearing testing, finding out what the hearing test or the audiogram says, and then you're going to be programming, because hearing aids are digital, you're going to be programming by Bluetooth on your computer the hearing aid so that the sound output from the hearing aid is giving more treble and less bass, because the guy has good bass hearing, lousy treble hearing. So that's how you prescribe hearing aids. And then you're actually going to be measuring what the ding-dong hearing aid is doing in the guy's ear. You're going to have a little tiny tube. It'll be in the guy's ear, connected up to a computer, and then you're going to put the hearing aid on top, and you'll be measuring the sound output from the hearing aid hitting the drum, the eardrum, and saying, hey, is that doing what it's supposed to? Yep, okay, save that. All right. So you got lots of neat things to learn in this field. I'm really looking forward to as we move on through, but right now I'll shut my face. I'm done. Have any questions? Email me. I check my OTC emails every ding-dong day, and I encourage everyone who's taking this course, check your OTC emails each day. Sometimes you won't hear anything from me for about a week, but then all of a sudden you might even get about 4 from me in a day, so it just depends. That's our best way to communicate. What does that movie say? What we have here is a failure to communicate. Anyhow, if you have any questions, do give me a shout that way, okay? All right. Live long and prosper. See you when we look at you. All right. I'll shut the recording down. Yeah, thank God I remembered to record. Any questions, Audra? Any of this is all good?
It's all good.
Cheers. Okay, good stuff.
Thank you.
Yep.